Hello students, welcome to the session. I am Mr. M.H. Mota, Assistant Professor, Department of Civil Engineering. This session is on the introduction to various RCC elements used in building construction. The outcome of this session. At the end of this session, you will be in a position to understand and explain various RCC elements used in building construction. We'll start the discussion with limitation of PCC. As we are aware, the plain cement concrete is weak in tension, though it has enough strength in compression. Due to its little tension carrying strength, the plain concrete as such is weak in bending, shear and torsion. Hence, the use of PCC or plain cement concrete is limited to such applications where the great compressive strength and weight are the principal requirements and where either the tensile stresses are totally absent or they are extremely low in the concentration. Because of that, the combination of steel and concrete becomes practicable and workable. The steel is strong enough to take the tensile stresses, and that's why the combination of steel and PCC has been proposed. The concrete while setting grips very fast the surface of the steel bars. Therefore, the concrete is able to transmit to the steel bars those stresses which cannot be resisted by itself. Or in other words, the concrete transforms the tensile stresses to the steel and compressive stresses are generally borne by the concrete itself. Again, the coefficient of linear expansion of concrete and steel are almost same. This particular coefficient is responsible for the change in the dimension with respect to change in the temperature. As we are aware, the increase in the temperature results in the elongation of the material, or the decrease in the temperature may contract it. But as the coefficient of expansion for concrete and steel are almost same, there is no relative change in the dimension with respect to each other as the temperature varies, because of which no stresses are set up within the RCC due to the variation in temperature. Again, the coating of cement grout on the surface of steel bars protect them from corrosion and does not produce any adverse chemical effect. The RCC. Concrete once set will take a superimposed load or the compressive load that compresses it, but will fail because of its weakness in carrying the tensile stress. On the other hand, the steel is strong in tension, and because of that the combination of these two material is proposed. The steel will bear all the tensile stresses while the concrete will bear the compressive stresses. Generally, the steel is introduced in that part of concrete where there is possibility of the introduction of the tensile stress, especially in case of beams and lintels. These kind of tensile stresses may develop because of the bending. Thus, reinforcement is used to help resist compressive forces or to improve its dynamic properties. The different elements of building made up of RCC includes roof slab, beams, columns, Pardi or a thin walls, lintels, Chajja, foundation, retaining wall, flooring and stair. We'll start this discussion from roof slab. The design of roof slab consists of thickness of slab, sizes of bar, spacing of bars, hooks, cranks and lap of bars, the amount of minimum cover to the concrete, etc. The mix of concrete for the slab is usually by volume and is proportionate to 1:2:4. Due to the loading conditions, the slab is subjected to possible of sagging or bending movement on the bottom surface at the center of the span and negative or hogging bending moments at top near support. To resist these moments, main reinforcement is provided at the bottom surface along the direction of span to resist positive bending moment. Depending upon the span, an RCC slab may be designed as either one-way reinforced slab or two-way reinforced slab. The slab which is supported on two opposite supports is called one-way slab. This slab is considered to be supported on two longer opposite sides. When the ratio between the length and the breadth of a room over which a slab is provided is more than 2, the slab is generally becomes one-way slab. It consists of main reinforcement spanning between the supports with distribution of reinforcement at right angles to it. The two-way slab is said to be spanning in two directions. This is generally the slab when the length to breadth ratio falls below 2. In such case, main reinforcement is provided in both directions in the form of a mesh. Bars smaller than 6 mm diameter or greater than 18 mm diameter are generally not used for the slabs. What we generally use are the 10 to 12 mm plain MS bars as the main reinforcement and 8 mm to 10 mm Tor steel bars as the distribution steel. They are provided at the bottom of slab, allowing a minimum cover of 25 mm. Next is beam. A beam is a flexural member and supports the imposed loads. The loads from slabs are generally bared by the beams. The most common shape of beam is a rectangle. In general, the width of beam is kept equivalent to the width of wall on which it rests. It rests means there should not be any projecting corners of the beams. Its depth depends upon the imposed loading. As the total load increases, the depth increases. Even its depth is equally varying with the span. The RCC beams may be singly reinforced or doubly reinforced. Singly reinforced beam means it has got the tensile stresses at bottom or the reinforcement generally available in the bottom part, while the doubly reinforced beam means it has got the main reinforcement at bottom as well as at top. For a wide and long hall, T-beams are planned at regular intervals. The beams and the slab in a T-beam are cast monolithically. This figure shows the cross-section of the RCC beam. It shows the main reinforcement, and at the center one bar has been shown which can be at the bottom at the central part of a beam, while at the support it changes its position from bottom to the top. This shows the cross section of T-beams. Well, this is an in general view of the general beam where the reinforcement has been embedded into the concrete. The red bars are the main bars, while the other bars are the distribution steel and the links or hooks which are provided to resist the shear stresses. The deflection. Deflection of a RCC beam or slab not only affects its appearance but also affects the erection of particles and interior decoration. This deflection is caused because of its own weight or by the excessive live load coming upon the structure or due to the effect of temperature, creep and shrinkage occurring after the erection. The total deflection due to all causes should not exceed 1 to 100 to 15 or 1 by 250 of the span length. The deflection of an RCC beam remains within the above limit if its span to depth ratio is 18 for a simply supported beam and 6 for a cantilever beam. Simply supported beam means a beam which rests on two supports, while cantilever beam is a beam of which one end is not supported, or it is supported only at the one end of the beam. For simply supported slabs, the same ratio should not exceed 36. For partially fixed conditions such ratio can be larger, expecting for a cantilever beam whose one end is always fixed. For spans spanning in two directions, the shorter length is taken for the calculating span to depth ratio. Column. A column may be defined as a vertical structural member subjected to axial load, whose length is more than twice the least lateral dimension. RCC columns are used to transfer the load of the structure over it to the foundation. It may be necessary to have a few RCC columns even in a small building. The size and shape of a RCC column will be determined by the architectural consideration as well as the structural design concepts. For individual columns, a minimum of 4 bars are to be used. However, if the load of column is very less, the columns are provided more from architectural point of view. In such case, 4 numbers of 10 mm diameter bars are more than enough. When a column is required to continue beyond a slab or through a beam, the main bars of a column must pass through a slab or a beam which frames up the columns. So this shows the cross section of different types of the columns. The column can be circular in nature, square in nature, or the rectangle in nature. While the reinforcement provided can be in terms of spiral reinforcement or in terms of even the rectangular hooks in case of other than main reinforcement bars. RCC lintels. RCC concrete is the most suitable and commonly used material for lintels in most of the buildings. It is resistant to fire, insects, temperature stresses and atmospheric agents. It possesses excellent resistance to tensile stresses with minimum size and is best suited for long spans and heavy loading conditions. They are much economical and easy in construction. RCC lintels have replaced all other material for lintels nowadays. The usual concrete mix for RCC lintel is 1:2:4. Some form of reinforcement is necessary in RCC lintels as plain concrete is weak in tension. This is the schematic representation of the RCC lintels. Next is RCC Chajja. Chajja is the projecting or overhanging eaves or corner of a roof, usually supported on large carved brackets for opening like windows. It usually protects the opening from external sunlight, from rainwater entering into the building. It also serves as aesthetic decoration with little design on it from the architectural point of view too. So this is the cross section of the simple RCC Chajja. Well, this is a photograph of RCC Chajja used in a building. Next is RCC Pardi. A 10 cm thick concrete wall reinforced with nominal reinforcement is called a Pardi. A reinforced concrete wall is designed as a compression member. The reinforced concrete wall is used in case where beam is not provided and the load from the slab is heavy, or when the masonry wall thickness is restricted. In such case, generally we used to prefer the RCC Pardi. This even can be used as the retention wall in case of underground construction. This is the cross section of a RCC Pardi used as the retaining wall in case of underground construction or in case of retaining a certain kind of material like soil on its either side. Next is foundation. RCC foundation or footing of superstructure using concrete and reinforced steel bars are very common in case of RCC structures or the framed structures. These are like a base for the structure above to distribute the load evenly from superstructure to the soil beneath. The different types of the footings includes individual footing or isolated footing, which generally supports one column, a combined footing which supports more than one column at a time, spread footing or strip footing, which are used to support the footings or the columns rather, which are placed in line, and those have been placed on a one strip like footing. Then raft or mat foundation, in which the whole structure has been placed along the one mat like structure or a common foundation. So this is a common foundation for whole building as such. Such kind of foundation are used in case of unreliable soils or soft soils. Then the pile foundations. These are used in case of very deep foundation where the hard strata is not available at lower depths. Next is RCC flooring. A reinforced concrete slab thin in section are used for exterior paving purpose, parking or base of basement tiles. This is a picture of RCC flooring where the whole floor has been made with the help of reinforced cement concrete. These are very common in case of parkings nowadays as well as in case of large factory buildings. Next is RCC stair. Stair is used as a mean of vertical communication. Stair connects the different floors or floors located at different elevations. RCC stair are not only structurally sound, but they are architecturally also very beautiful. It can be molded into any required form and can be constructed with structurally sound expectation of the performance. So this is it for this session. Let's meet in the next session to know more. Thank you, and don't forget to like, comment and subscribe. Don't forget even to share it with all budding civil engineers. Thank you.